matrices, or I can state it with L. Okay. Yeah, what is preferred? What I want to come to now is the spectral theorem.
Matrices, I think.
Matrices are better. Okay. Okay. So let's then come to the spectral theorem. I will first state it completely in terms of matrices and then say what it means in terms of linear transformations. Okay. So spectral theorem for this is the single most important theorem that you will learn in linear algebra class. Okay. So let's pay attention to this. Quite often this comes kind of towards the end of the course, and what I find is, at least among students, many a time they don't appreciate this. This is an extraordinarily important fact. Okay. So let A be an n cross n matrix, complex matrix, such that A star is equal to A, which just means Aij is Aji conjugate. Okay. So then the statement is orthonormal basis of Cn consisting of eigenvectors of A. This is one fact. Fact 2, which I could have done earlier, is the eigenvalues of A are real. Okay. So even if though it's a complex matrix, the eigenvalues of A are going to be real, and there is an orthonormal basis of Cn consisting of eigenvectors of A. So to write in words, there exists V1, V2, Vn, which is an orthonormal basis. Okay, no need to write. I think the sentence is self-explanatory. There's an orthonormal basis of the underlying space such that all the basis elements are eigenvectors of it. Okay, so this is the most important theorem in in linear algebra that you learn. Okay, so there are many different ways to state it, but maybe let's just go over the reasoning why this is true. Okay, or which should I do first? There are multiple ways to state it. Okay, so there are many ways to state this. Maybe we understand it in okay. So, but before that, let me just finish off the proof for the second one. Okay, so let me prove this. This is actually somewhat easy. So that we just recap also the definition of eigenvector. So suppose lambda is an eigenvalue. With eigenvector, there can be many eigenvectors for lambda with an eigenvector v, suppose. That means AV is equal to lambda v. How do you show lambda is real then? How do you show lambda is real?
We will take adjoint on the both sides.
Okay, you multiply by the adjoint. Okay, so you want to multiply by A star. Is what you're saying? Yes.
Okay, using inner product we can prove.
Okay, so maybe this is a good idea, but maybe an easier, or I don't know if that works, but yeah. So inner product with what?
Lambda times inner product of v comma v equal to.
Okay, so you multiply, right? So you multiply by v star. If you want in terms of matrices, I can write here in terms of linear transformations. So you do v star AV. is equal to lambda V star V. V star V is just the inner product of V with V. Okay. So this is true. Then what?
We use A star equal to A.
Sorry.
A star is equal to A, so one can make use of that.
So this is lambda times summation mod Vi square by the way. So this is lambda times. So, but what is V star AV?
V star A star V, so that is AV star.
Okay, you could do that, but without doing that, let me just write here. So this is Aij Vi bar Vj, right? So when you are multiplying by V1 bar up to Vn bar, and then A, and then V1 up to Vn, you just multiply out. You will see that it is Aij Vi, the ith element here and the jth element here. Okay. So which you can write as, so let's take the II case separately. Aii Vi absolute square, right? I equals 1 up to n. If you take I equal to j, those terms will give this. And then let's take the I less than j terms. I less than j terms will give me what? Aij Vi bar Vj. But I also add the other one, Aj Vi Vj bar. Is that okay? I'm just writing Aij Vi Vj. So I equal to j terms I'm writing here. For I less than j, I'm writing the ij term as well as the ji term. Is that okay? Now what is this? What would we know about this? What is Aji? Aji is same as Aij bar. So this thing is the conjugate of this. See, this is the conjugate of this. So far I have not used the fact that A star equal to A. Here I am using A star equal to A because Aji is Aij bar. The conjugate of this whole thing is this. So this is conjugate. So what is this? This becomes Ai mod Vi square plus sum over I less than j 2 times the real part of Aij Vi bar Vj. Because if you add a complex number to its conjugate, you get 2 times its real part. So what happened is that lambda times this number is equal to a real number. This is real. Second part is real. The first part is also real because Ai equal to Ai bar, this is also real, right? So whole thing is real. So if lambda times norm V square is equal to a real number, which implies that lambda belongs to real. Is that okay? So usually you will find it written in a much shorter way. Okay, like somebody suggested the trick that you should write this as V star, A star, V and so on. But then what I wanted to convey by this is that you don't necessarily have to do things in the cleverest way. Okay, you try to do what you can, and many a time you will arrive at the result anyway. So you just, you don't have to be clever. V star A, V, you just write out what it is and then arrange it. Then you see that it's a real number. If lambda times a real number is real number, then lambda also must be real number. Okay, so this is why, even though maybe it is a little longer than the way proof is presented in books, I presented it this way. Is that okay? Any questions here? Are there any questions? No?
No, sir.
Go ahead.
So no questions. Thank you.
Questions? Okay. So this is showing that all the eigenvalues are real. This was apparently first proved by Kosuhik. Okay, it was not something that was realized before. But now the fact, the very, very important fact is that the eigenvectors of A can be chosen so that it forms an orthonormal basis. Okay. So there are many other ways to state it. So let me state it in other ways. So first, let me state this same way. So first one is, there exists V1, V2, Vn orthonormal basis of Cn such that A in a Vi is lambda I Vi for some lambda I in R. These are the eigenvalues, of course. Okay, so this is just the same thing that I have stated here. Okay. So this is the same as what I have stated here. I have just written it in symbols. There I have written in words. Here I have written in symbols. There is an orthonormal basis of Cn such that AVI is lambda IVI. Second way is writing it as I can write it as A is lambda 1 V1 V1 star plus lambda n Vn Vn star, where again lambda I are eigenvalues, Vi are eigenvectors, and AVI is lambda I here. Okay. So these are orthonormal basis, and these form an orthonormal basis. Okay, so this is how you can write it. Why is this the case? So you see how A acts on any vector. See, AVI is lambda IVI, right? So from that, we can write it in this form. Why is that? Why is that? Maybe I give a quick reasoning here. See, suppose you know that AVI is equal to lambda IVI and VI form an orthonormal basis. Then, if I want to apply V to any vector, what do? First, I write V as in terms of the VIs, right? Summation alpha I VI. I equals 1 to n, where alpha I is V inner product VI. This is how you expand V in terms of the VIs, right? And then I apply A to that. So what is that? It is summation alpha I AVI. I equals 1 to n by linearity, right? But what is AVI? It's lambda IVI. So this is just summation alpha I lambda I VI. I equals 1 up to n. Is that okay? So what is this one? So let's take this one. Let's call this matrix B. What does B do? You see the same with against B. What happens if I apply B to V? Okay, so B is lambda 1 V1 V1 star plus lambda n Vn Vn star, and you are acting on alpha I Vi. Actually, I need not have done this much, but it's okay, not a problem. What happens when I multiply V1 V1 star against this? See, V1 star Vi is 0 if I not equal to 1 and 1 if I equal to 1, right? Because they are orthonormal. Therefore, the first one, when you apply V1 star, you multiply here, you will only get alpha 1 V1. Second one, when you multiply, you will just get lambda 2 alpha 2 V2 and so on, which is same as this. So this other matrix and A are the same thing actually. So this is related to what one of you asked. This is writing in terms of the projection matrices actually. Okay. So let me write one more way. So these are actually projection matrices. V1 V1 star is the projection onto span of V1. Okay, V2 V2 star is the projection. So you are writing the matrix as a sum of projections. Not only sum of projections, these projections are themselves orthogonal to each other. They are to orthogonal subspaces. That is the important thing. So yet another way to write it is, sometimes these eigenvalues may be the same. So you can club them together if you want. You can write it as mu1 p1 plus up to mu k pk, where pi, p1, p2, pk are projections such that onto orthogonal subspaces. and mu I are mu1, mu2, mu k are distinct eigenvalues. You can ignore this third one. It's not so important, but the point is sometimes lambda i's can be. So there was a simpler way to say the spectral theorem. I could have said, let A be a self-adjoint matrix, then the eigenvectors of A form an orthonormal basis. Why did I not say that? Okay, why didn't I say the eigenvectors of A form an orthonormal basis? Yes, anyone?
Sorry, sir, can you please repeat it?
Yeah, so this one looks a little convoluted way of saying. I could have stated in a simpler way. I could have said, let A star equal to A, then the eigenvectors of A form an orthonormal basis of Cn.
All eigenvectors need not be an orthonormal basis. It need not form an orthonormal basis.
Why? Can you explain what you mean?
If lambda is eigenvector, then scalar times that is also an eigenvector.
Right.
That inner product need not be equal to 1.
That is true. That is, but even more, that is a good point. Of course, when I say eigenvector, there is a matter of choice. Okay. But to get orthonormal basis, of course, I have to normalize them to have unit norm. Otherwise, it won't become orthonormal. This is a good point. But something more, is there further choice in eigenvectors? The thing is, if some eigenvalue has multiplicity more than 1, okay, then there are many ways of choosing eigenvectors. So for example,
Linearly independent.
So the thing is, there are different ways of choosing eigenvectors. So for example, if you take the identity matrix, if you want orthogonal eigenvectors for this, you can pick any u and v. Okay, so I can take this and this, x-axis, y-axis, or I can take this. Any pair of orthogonal vectors will give me an orthonormal basis of eigenvectors. So that's not uniquely defined. Okay, eigenspaces are uniquely defined. Eigenvectors are not uniquely defined. So these are projections onto eigenspaces. That is the reason why I did not say it like that. But these are different ways of thinking. Geometrically, what it is saying is the following. Let me end with that, one more minute. So what is it? What is the geometric meaning of this? Oh, okay. The most important, another way, which will lead to that, is in terms of matrices, we can state it in yet another way. This is, of course, related to the diagonalization of matrices. So we can write A as x d x star, where D is the matrix of eigenvalues, diagonal matrix of eigenvalues. This is diagonal. And what is the matrix X? It just has the vectors, eigenvectors v1, v2, vn, an orthonormal basis of eigenvectors. This is a unitary matrix. So X star is also X inverse there. This is actually yet another way to say the same thing. If you write down this in terms of this is actually yet another way to say exactly the same thing. This one you can relate to point number 2 or many other ways. It's a good, now I don't have time to go over all the relations, but it's good to understand it in all these ways. So A you can write as a diagonal unitary times diagonal times unitary. Okay. So geometrically, what all this means is the following. Geometrically, what is it saying actually? So take a matrix. So suppose A is a 2 cross 2 matrix, which is like this 2, 1, 1, 0, let's say. This is a symmetric matrix, right? Which is Hermitian. So this is complicated. If you apply it to 2, 1, 1, 0 to x comma y, what it is doing is 2x plus y and y. Okay, so this is something a little complicated. What the spectral theorem is telling is that if you look at the eigenvectors, if you look at the eigenvectors, they will you can get an orthonormal basis. Let us say this is V1 and this is V2. Okay, so this is the direction of V1 and this is the direction of V2. What in that basis, it is very, very simple. A acts very simply on this by lambda1 V1. A acts very simply on V2 by lambda2 V2. So what it does is, in this direction, it is stretching by lambda1. In this direction, it is stretching by lambda2. So you can just think of your, in this basis, it becomes diagonal and it is just stretching in each direction. That is the geometric meaning. So a diagonal matrix, if I have some 2, 1, 3, what does it do? It just stretches in the coordinate direction. In the x direction, it stretches by a factor of 2. In the y direction, it just keeps it as it is. In the z direction, it stretches by a factor of 3. So every symmetric matrix or Hermitian matrix, it looks complicated if you write it in usual basis. But the point is, there is a basis in which it looks extremely simple. It is just stretching in an orthogonal direction. That's what the meaning of spectral theorem is. Okay. Sorry, I went over time. One last point that I want to just say is that this is the use one to relate to the first thing that I was saying. When you write x d x star, one simple use of this is that you can take very high powers. If I want a to the 10, I just write x d x star, and so on 10 times. What happens is x star x is identity, x star x is identity. So this just becomes x times d to the power 10 x star. And it's very easy to raise a diagonal matrix to any power. You just raise all the entries to the power. So this is one of the problems, if you remember the Fibonacci problem, and we wanted to raise a matrix to a very large power. And if it's a symmetric matrix, this is our Hermitian matrix. This is telling you spectral theorem. You find the eigenvectors, eigenvalues, and diagonalize it. Then this job becomes easy. Okay. Okay. Sorry for going over time, but since this was the last lecture, I did that. So yeah, if there are any questions, I can answer. Otherwise, it ends here. So next week, Venkatesh will come, or next week, or whenever it is.
Yeah, so this was the last lecture for Manjunath for this workshop. He will be here with us for the rest of the workshop, but I think he won't be lecturing anymore. So thank you for this wonderful set of lectures. I'm sure all of us had a very nice time. It was quite exciting to learn how eigenvalue comes naturally to compute a term of a Fibonacci series, and how matrices come up when we try to compute the number of k-walks, and taking us through this whole journey of linear algebra ending with spectral theorem. It was really nice. We enjoyed a lot. If there are any participants who would like to say a few words, you are more than welcome.
Yes, sure. This is Nayan. I'm an assistant professor at St. Joseph College. In fact, I'm colleague of Professor Sushobhan. I'm really thankful to him for allowing me to attend this lecture. I must say that Professor Manjunath, he has done quite well. Actually, I enjoyed his lectures throughout the lecture. I enjoyed. It's a good start. I am thankful to Professor Manjunath as well. Yeah, thank you.
Yeah, thank you all for attending. So Venkatesh will continue with some canonical forms and stuff like that. But again, if you wish, again, as I said, we'll take feedback, particularly after now that 1 week is getting over, maybe tomorrow, day after, sometime we'll ask for feedback. Please do give so that your experience can be improved in the next 2 weeks. Okay, so that it will be actually useful. This is one thing much more difficult to know in online forum than if it was physical. Don't know exactly if what we are saying is being conveyed. So yeah, feedback will be useful. Anyway, thanks everyone.
Yeah, does anyone else wants to say anything?
Yes, this is Shubhojit Pal. I'm from Shiliguri. So I liked Professor Manjunath's lectures a lot. I mean, at this level, when I'm talking to a group of teachers, it is not easy to motivate them with new perspectives and examples. So the very first lecture where he did it with the Fibonacci sequence and all this stuff. It was really good, and the level at which he delivered his lectures with the trivialities left to the audiences and with the actual important things being all covered up, that was really commendable. And thank you, sir. Thank you so much for this.
Thank you. Thank you.
Thank you. Okay, I think Kosuhik, is it okay we start at maybe 7:15? It's 7:10 now. Is that fine? I mean, we will be 5 minutes late. Yeah. Okay.
Sure, that's fine.
Okay, so let's have a quick 5 minutes break. We will start at 7:15.
Yeah. Sorry, Kosuhik, this last lecture went a bit over.
No worries, Manju. I'm doing that every day. So
No, but for you, it's okay that after, yeah.
no worries. Yeah, it's fine.
Yeah, I think we can start now. Hello, Kosuhik.
Kaushik, you are muted.
I think there must be some internet issue. I think he's not there in the meeting now. I think he will be rejoining soon.
Yeah, probably.
Yeah.
Yeah, sorry.
Yeah,
My
no
laptop.
problem.
Yeah, my laptop froze, so I had to join from my iPad. So yeah.
Okay, no problem.
Okay, let me share my content.
Yeah,
sure. It says I haven't been made host yet.
Can you try again? I just.
Yeah. Okay.
Yeah, okay.
Yeah. Okay. Okay. Can you see my screen?
Yes.
Yes, sir.
Okay. Okay. So let me just remind last time what we were doing. So today the final lecture of the first week. But so last time what we did was that we started towards the end, we started series. So what does it mean to say that a series converges? So if you have an infinite number of terms, you want to somehow make sense of adding them up and getting some a number, then the most natural approach is to take that take the sequence of partial sums. If those converge to some limit, then we say that the series converges. And we saw that some basic things, and the most important series is this geometric series. So this is if mod lambda less than 1, this infinite series not only converges, we also know the exact value, the value of the limit of partial sums, that is the value of the series. So we know that in this case, it's exactly 1 by 1 minus lambda for mod lambda less than 1. And then since we did Cauchy sequences, we know that for a real sequence, it converges if and only if it's Cauchy. So therefore, we can now transfer this to series and say that series will converge if and only if Sm minus Sn is small for m and n large. Okay, so this translates to k equal to you sum from m to n ak or m plus 1 in this whatever you want. So that that is less than epsilon. Okay, this is the Cauchy criterion. It's quite an important way to show that series converges. And as a result of this, we showed that necessarily, if a series converges, then necessarily the individual terms should go to 0. Okay, so mod an goes to 0 if an converges. And then we saw a basic example of some series where the terms do go to 0, but the series diverges, which is 1 by n, the series 1 by n. This we show that S2n minus Sn was at least half. Therefore, it cannot be Cauchy. And finally, we did this comparison test. If Bn converges, Bn is a non-negative sequence, the series Bn converges, and if Bn dominates mod An, then the series An also converges. Okay, this we showed by application of the Cauchy criterion. Okay, so this is where we will continue. Yeah, so maybe I will move to the new notebook. So today I plan to continue with this comparison, give you a few examples, and maybe I'll just try to do this ratio test. And if time permits, I will start with some continuity. I don't know if I'll have the time. That's why I put a question mark. Let's see. Okay. Yeah. So the first thing I will just remind. So let's see that. Yeah. So if sequence. Or let me say, let An be a sequence, real sequence. If the series modulus of An in going from 1 to infinity or 0 to infinity, if the series mod An converges, then we say this one, the infinite sum An converges absolutely. Okay. So this is our terminology. If instead of just requiring that An, the partial sums of An, if instead of that, if you say the partial sums of mod An converge, then we say that An converges absolutely. And in fact, this, if you look at the previous thing, what we did, that this Cauchy thing. So if you look at in particular this kind of inequality, if mod a series mod An converges, then that the leftmost, let me just underline it. So you just look at these two together tell you that if mod An converges, the series, then An also converges. Okay, so I will just so just fact. If An converges absolutely, then the series just converges, right? Okay, simply because An is, you can think of it as An, the Cauchy sum for that is bounded by the Cauchy sum for mod An. Okay, so we will continue with this comparison just to tell you. So as I mentioned, in series, the most important two things are the geometric series and the comparison result. Nearly everything in series follows from these two. This is something you should keep in mind. Okay, so let me write the contrapositive, another way to write this thing. So I will write this, the contrapositive of this comparison thing. Comparison result. So suppose you have two non-negative sequences. Let An and Bn be two non-negative sequences. Suppose we know the series Bn, the infinite sum Bn, if this diverges and we have An bigger than equal to Bn for all n, then the series An also diverges. Okay. So this is the, so if you restrict yourself that both sequences are non-negative, suppose you know that one of them, Bn, the series Bn diverges and you have this inequality, An dominates Bn, then the an should also diverge. Okay, so this is just another way to state this comparison, right? Because why is this? Can someone tell me quickly why this follows from the previous one? Anyone? So I am not checking my chat. I'm on my iPad. So if you can just unmute and say, then. Can you hear me?
Yeah, yes, we can hear you.
Yes, yes.
Yeah. So why is this true? Then if Bn diverges under these conditions, then An also diverges. How does this follow from something we just did?
Because the sequence of partial sum is monotonically
Okay.
increasing and it is unbounded.
Okay, but we want to just, yeah, I mean, I just want to state this in a way that it follows from the comparison result, which I did yesterday, right?
Can we take the negatives?
Negatives.
Multiply
Okay.
the previous inequality by -1, so the sign will change possibly.
No. I mean, yeah, comparison test. Yeah,
Sir,
you
sir.
cannot. Okay.
Sir?
So one, yes.
Sir, if summation A and G converges,
Yeah.
then automatically summation B and also converges.
Yeah. So this is that's why I've written it's the contrapositive. Suppose you assume, so this follows directly from the previous one. Suppose you assume that this series An converges. Okay. Remember, An and Bn are given to be non-negative. Suppose you assume this converges, then since An is bigger than equal to Bn for all n, then comparison tells you sigma Bn also converges. Okay, but we are given that in fact we are given that this series Bn diverges, so you can't have this. Okay, so comparison you can only so we will see actually. So comparison, someone said, can we multiply negative and so on? So you have to be very careful when you do comparison. This is not generally true for if the sign change happens, if the sequence. So you let me just go back to yesterday's comparison, what I stated. Yeah, so you see that Bn is a non-negative sequence. And we are saying if mod An less than equal to Bn, everything here is non-negative. Okay. If you just assume you can't write comparison for things which change sign or which may be negative. So for instance, so watch out, let me write, watch out for sign changes in comparison test, because you can give very trivial examples, right? -1 by n is always less than equal to 0. Okay. Of course, we expect this series, this should always, this converges to 0. But -1 by n, just by algebra of limits, we saw yesterday 1 by n diverges. So -1 by n also diverges. Okay. So you have to be careful. You cannot do comparison tests for things which are negative like this. So in general, you have to prescribe something. Okay. Yeah. All right. So let me just do a few examples. So just to tell you the power of comparison and geometric, if you combine the two, then how much you can do. Okay. So let me just do a few examples. I think most of the lecture will be covered by this. I don't want to really focus too much on, see, it's fine if you want to quote root test or ratio test and so on. But instead of just remembering and not remembering the result and not knowing why it works. Okay. So just to illustrate that this is the main comparison and geometric series are the main. Let's do a few examples, which we won't use any this root or ratio. Okay, let's do a few things. So maybe let's take 1 by n factorial. Okay, so of course, everyone knows that this is how we define, or this is one of the ways we define the number E. But let's not worry about that. Let's say, how do we know that this converges? Just purely based on what we have done. Okay, any ideas?
Sir?
Yeah.
So 1 by n factorial is less than 1 by 2 to the power n minus 1.
Yeah. Okay. So this is gives you immediately this this inequality someone mentioned. So let me just write it. So what we have is, so how large? So you have to get an idea of qualitatively how to estimate these things. So n factorial is at least 2 power n minus 1. This is true for all n. Okay, why is that? Remember, n factorial is n times n minus 1 blah 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 times 2 times 1, right? So after the second term, so starting from here, every other term, so you have 3 is bigger than equal to 2 and so on. So each of the terms starting from the second one is bigger than 2. There are n minus 1 of them. So you have this. Okay, in fact, you can do a little bit, of course you can do way better, but you can also write n factorial bigger than 2 power n, except you have to now write this for n bigger than equal to what, 2 or probably 4. Yeah, 4. Okay, yeah, anyway, this is always true, right? Everyone agrees with this. So in series, main thing is how to estimate. You have to get a sense of how big is the quantity. Hopefully you can estimate it in a way that comparison tells you. Okay, so n factorial is bigger than 2 power n minus 1. Therefore 1 by n factorial is less than equal to 1 by 2 power n minus 1. Okay, but we know that therefore comparison test. See, remember that geometric series, so the series 1/2 power n going from 0 to infinity, this we saw yesterday, this converges. I'll write less than infinity. So if you start the left hand side, the right hand side at n equal to 1, that converges. So this therefore comparison tells you this also converges. Okay. Okay. And some questions? Okay, so let's look at some other example. So let's maybe look at something again here like this. So let's say n plus 2 by something like n squared, maybe 3n plus 1. Okay. So this is the infinite series, n equal to 1 to infinity. We want to decide whether this converges or diverges. Okay. So let me pose a question: converges or diverges? Which one is it? What do you think? I mean, you should think of how the terms behave. How is it behaving? And then, so guess first and then try to prove it rigorously. Okay.
Divergent.
Divergent. Okay. Someone said divergent. Okay. So just tell me roughly, how does this sequence behave? This n plus 2 by n squared plus 3n plus 1. Why is it divergent? Or maybe let me ask this way. Why is it divergent?
Comparison test, by comparison test.
Okay, very good. Comparison with?
Is less than or equal to 1 upon n.
Okay, that may not quite, that doesn't quite work, right? So we saw yesterday that, see, the series on the right hand side, if that converges, then comparison says that the left hand series also converges. So 1 by n diverges. Therefore, that comparison does not say anything. So any series is less than infinity. So that's that less than equal to infinity. That's not useful for us. So you said it's divergent. So how does one prove that?
Limit comparison test.
Yeah, that's what I'm saying. Limit comparison. Yeah, I don't know what that means. What is limit comparison? Or whatever. Let's say you use comparison test, whichever way you want. But what do you compare it with?
It is greater than 1 by n.
Greater than 1 by n.
Yeah.
Okay.
We can prove that the numerator is greater than n and the denominator is greater than n square.
Yes,
okay.
Greater than 1 by n.
Okay, so let's check. So it's okay to play around with these kind of things. Okay, so someone claimed, we'll just check whether this is true. This is true for, is it true for all n or for, let's check anyway. Is this true? Then you play around with this. So n squared plus 2n, if I just clear denominators, I will write here, is this bigger than equal to n squared plus 3n plus 1? Okay, so n squared cancels. Is 2n bigger than equal to 3n plus 1? No, right? That means n is less than equal to minus 1. So this is not true. Is everyone with me so far? So just a simple thing that if you just try to lower bound it by 1 by n, this does not work because this inequality is not going in the right way. Okay.
1 by 4n will work, I guess.
1 by 4n. Yeah. Okay. So that idea is nearly right, but you have to be careful. Okay. So in fact, what works? So let me write here. This doesn't quite work, but as someone mentioned, 4n or 2n even works. Okay. But this works. So n plus 2 by n squared plus 3n plus 1. It is indeed bigger than, let's say, 1 by 2n. Okay. Again, why is this? We have 2n squared. If you clear denominators, 2n squared plus 4n, is it bigger than equal to n squared plus 3n plus 1? Okay. So what does this mean? That means, is n squared plus n bigger than equal to 1? This is always true. Okay. Is this okay?
Yes, sir.
Yes, sir.
Yeah. Okay. So the thing is, first you guess. Okay. N plus 2 for large n, it behaves almost like n, and denominator behaves like n squared again for large n. So roughly the ratio should behave like 1 by n, right? But when we try to prove it rigorously, this does not, we see this bound doesn't work. So if you just modify a bit, just make it 2 here in the denominator, then you're able to prove the result. Okay. So now the contrapositive of the comparison, what we wrote. Okay. Contrapositive of comparison. So we know that the series 1 by 2n, n equal to 1 to infinity, this diverges. We have seen this. Again, I proved 1 by n diverges. Therefore, so following algebra of series, algebra of limits. Okay. So 1 by 2 times n diverges implies this n plus 2 by n squared plus 3n plus 1 also diverges. Okay. So in here, the question was posed, this is divergent. Okay. Okay. So do you have any questions with this?
No, sir, it's clear.
Okay. Okay. So maybe we just look at some other example. Okay. So maybe we look at one last example. We go before I go to more familiar series. So let's look at. So all these things, both the series that I wrote, 1 by n factorial, n plus 2 by whatever, all these were positive numbers, positive sequences, right? So let's take something which may not really be. So let me write, we actually dealt with some sequence like this, cosine n pi by 8 or something. Let me just make it even more complicated, e power n by 2, blah, blah, blah. And then, okay, I have not done this yet, right? Okay, so yeah, maybe let me just come back to this. But yeah. Okay, so maybe now I go to so let's do 1 by n power a. So for which a question, so of course everyone has seen this, I suppose. So for which real numbers a does this converge? Okay. So let's try to do it. Certain classification is easy. One of them is direct. So if a is negative, then the series diverges. Why is this? Just one word. Why is this divergent if a is negative?
Because the power is there is negative in the denominator that comes up in the numerator, then it becomes.
Cannot partial sum diverge.
The term limit doesn't go to 0.
Exactly. Yeah. So if a is negative, then because 1 by n power a is bigger than equal to 1 in this case.
Yeah,
Okay.
means sir, every terms of the sequence is greater than with some positive number.
Yeah, it is great because it's negative. So it's like, so every number is in fact bigger than 1. So terms don't go to 0. Okay.
And
So yeah. Okay. So it for a less than 0, it diverges. That's okay. This is a simple reason. So let's do 0 less than a less than equal to 1. Okay. Then what happens?
Again, diverge.
Okay. It diverges. By why do you say so?
Comparison with the harmonic series.
Yes, sir.
Okay. Yeah. Yeah, that is correct. So series diverges because, so we have 1 by n power a is bigger than equal to 1 by n. Okay, for all n.
Excuse me, sir.
Yes.
Sir, can we say as an does not tend to 0? That's why, because that is the necessary condition, na?
Yeah,
For
that's
it
what
to
I've.
be convergent. An
Yeah,
tends
that's.
to 0.
Yeah, that's what I've written here. No, that 1 by n power a. In this case, it's bigger than equal to 1. So maybe right. Let me just finish it. So terms don't go to 0. Okay. So in the second case, when 0 less than a less than equal to 1, the series diverges because we have the contrapositive of the comparison. Okay. So 1 by n power a, it's bigger than equal to 1 by n. Okay. Again, this should be fairly obvious. Remember, a is less than equal to 1 and positive. So a is less than equal to 1. So n is bigger than equal to n power a, and therefore you get, when dividing, you get the other way around. Okay. So again, a contrapositive. So use contrapositive of comparison. Okay. But how about a bigger than 1? So how about for a bigger than 1? So we have 1 by n power a for a bigger than 1. Does it converge or diverge?
Yes, convergent. By
Convergent.
comparison test.
Okay. Someone said by what reason?
Comparison test, because n to the power a is always greater than or equal to something.
No, remember,
Not
if you
really,
say
actually.
if you say convergent, then you should dominate. 1 by n power a should be less than equal to something that you know converges.
Convergent,
Okay?
yes.
Less than or equal to 1 upon n square, I think.
Well, that is also not true. Remember, we are claiming this for all a bigger than 1. First of all, we haven't showed that 1 by n square converges. This is part of the problem, no?
Yes.
A is 2, we have to show first. Okay. So converges or diverges. So let me write it. So there are several ways to do it, but I just want to focus just on the basic things. What we have done, that's already enough to prove this. One has to be a little bit more clever with this one than the previous things. So I will do the proof. Okay. So it converges. Why? So remember, this is a series in which each of the terms is non-negative, and we have shown already enough to show. So yesterday we did this, enough to show, not shown, show that the partial sums are bounded. The sequence Sn, right? If for non-negative terms, the series converges if and only if the sequence of partial sums is bounded. So that's what we will show. Okay. Okay, even this directly we are not going to show the whole thing is bounded. This is a good thing in analysis where you will let me finish writing the proof, then you see what is at play here. Okay, how do we show that Sn, the sequence of partial sums, is bounded? So let's try to again play around with this thing. Okay, so what is this? S1 is what? S1 is only 1. Okay, that is fine. We can write less than equal to 1. Okay, so maybe I write a little bit, yeah, so maybe I start with this actually. So let's say 1 is less than equal to 1. Then I have the, let me write the second things, 1 by 2 power a plus 1 by 3 power a, okay? So forgetting the first term, 1 by 2 power a plus 1 by 3 power a, you all agree that this is less than 2 by 2 power a, right? Because 1 by 3 power a is less than equal to 1 by 2 power a. So already there is another 1 by 2 power a. So therefore you have 2 by 2 power a. Is this okay?
Yes, sir.
Okay. Let's yeah. So now let's look at the next one. Okay. 1 by 4 power a. We are not considering directly partial sums. I'm just estimating terms which start with the power of 2. But I am estimating blockwise. Okay. So let's do this. 4 power a, 5 power a, 6, and then stop before the next power of 2, which is 8 is the next power. I stop at 7. So this is, if you bound using similar one like previous one, all of this is less than 4 by 4 power a. Is this okay? Because each of these terms, each of them less than 1 by 4 power a. So 4 by 4 power a. How much is 4 by 4 power a? This is exactly 2 by 2 power a squared. Yeah. Is this fine?
Right, sir.
Okay. So if you continue, so maybe I'll just write one more. If you write 1 by 8 power a, so where should we stop here? If you want to estimate, just like we did previous 2 lines, where should we stop?
15.
Yeah, 15. Yeah, 15. 1 by 15 power a. So how many terms are there? 8 terms. Each of them is less than 8 power a. So we have this. This is exactly 2 by 2 power a cube. Okay. So if you, whatever we have done here, so let me just mark it in red. So like this, if you proceed, what we get is the following. Proceeding like this, we get, so if Sn is the sequence of partial sums of this 1 by n power a, you get S, let me write here, 2 power k minus 1. Okay. So let me write it and then I will ask you whether it is clear that this is happening. 2 by 2 power a to the power, let me write m. M goes from 0 to k minus 1. Okay. See, all I'm doing is I am just adding all of these. So maybe each of these things I will circle in red. This is the second estimate, third estimate. Is this clear to everyone based on what we have just done, the previous 3 lines? So you compare. If k is 1, then you get just S1. S1 is only 1. So 1 less than 1 is satisfied, right? If k is 1, then m should go only one index, 0 only. So 2 by 2 power a power 0, which is 1. If k is 2, 2 power 2 minus 1, S3. S3 means 1 plus 1 by 2 power a plus 1 by 3 power a. You combine these 2 inequalities. It is less than 1 plus 2 by 2 power a, which satisfied for k minus 1. Okay. So I hope that you can convince yourself by induction that this is true, right?
Right, sir.
Is everyone okay with this?
Yes. Okay. Yeah.
Okay. Okay. But remember, what do we have? We are dealing with the case when a bigger than 1. This you should keep always in your mind. So 2 by 2 power a, what can you say about the size of this?
It is less than 1.
Yeah, it is definitely less than 1, right? So we can write 2 by 2 power a. Let me say it is some lambda less than 1. Okay. So what we can say, S 2 power k minus 1. This is true for all k bigger than, so I have written here for all k bigger than equal to 1. This is definitely, we know that the series converges, right? Lambda power m converges. So less than, let me just write 2 by 2 power a power m, where m goes from 0 to infinity, right? I've only added more non-negative terms. I know that this series, this is convergent. So this has a finite limit, right?
Yes.
So you see what I've done? So this one, it stops at k minus 1. So therefore, definitely this term is less than equal to the infinite sum, which we know that the infinite series converges because a is bigger than 1. Okay. So what we have done is S2 power k minus 1. This is bounded above, right? This is a number which is not dependent on k. This is some number. Let me call it m. Okay, capital M. Okay. Now we have shown S2 power k minus 1 is bounded above by m for all k. So that means what? Just to, we have S1, S3, S5, not S5. What is it? 3 minus 8 minus 1, S7, S15, blah, blah, blah. All of these are bounded above by m. So somehow we want to conclude, somehow from this, that Sn is less than equal to m for all n. How do we go from only 1 less than powers of 2 to all natural numbers? Any ideas? How can we do this?
Sn is increasing.
Yeah, so Sn is increasing, that is correct, yes. So, but just to, kind of ask you for a little bit more detail. So from there, how will you conclude?
It is a subsequence of his Sn.
Subsequence. So why is, yeah, sorry, can you tell again about the subsequence? I didn't get your answer.
Oh, so I'm connecting the dots. So actually, I'm seeing that this is the subsequence of Sn.
Sir,
Okay.
what we can say, if all subsequents are bounded, then the main
Yeah.
sequence is also bounded. This
Okay,
is for
but,
all k we are saying.
Yeah, but that is not all subsequence, right? This is one particular subsequence.
Okay,
S2
sir,
k,
the
yeah.
subscript is 2 raised to k minus. Yes, correct.
Yeah, so that is one subsequence.
Yeah.
We have to somehow say from there bounded,
By-
from that one, yeah.
By
By
contradiction.
Archimedean property, for every n there is some number k, so that 2 to the power k is greater than n, and s2 to the power k is smaller than m. So
Yeah.
Sn must
Yeah,
be
that,
smaller.
yeah. So the thing is that, yeah, so that is the correct way to do this. So notice, so let me just write this. Notice, for any n, okay, there is there is a k such that, so for n, let me erase. For every n, we have 2 power k, we have a k, we have a k such that n is exactly between consecutive powers of 2, right? So you pick the, like someone said, so you can pick the first power of 2 that is bigger than n, okay? Then it will have this property. Is this okay? So any power, any integer, any natural number lies between 2 consecutive powers of n, okay? So what we have here, so Sn, because the terms are non-negative, therefore Sn, someone said the sequence of partial sums is increasing sequence. So definitely for such Sn, for such n, Sn is less than equal to S2 power k plus 1 minus 1. Is that okay? So n can go less than 2 power k plus 1. That means the next best it can be 2 power k plus 1 minus 1. So for such n, we have this. But we know all such partial all such partial sums are bounded by m. Okay, we have shown here for any power of 2 minus 1 difference, that is bounded by m. So this implies Sn is also bounded by m. This is true for all n. Okay.
Professor Kosuhik, can you please repeat it? So,
so this is okay. The star that I have written, is this fine?
Yeah, that's fine.
Okay. If this is okay, so you agree that the sequence Sn, this forms a increasing sequence because all the terms are non-negative.
Yeah.
So Sn will be less than S2 power k plus 1 minus 1. If n is lying in this range, then is this not true?
Okay, okay, yeah, fine.
Okay, but for all these kind of things, we have shown already it is at most m for any power of 2 minus 1, right?
Yes.
So we have Sn less than equal to the sum, same thing, m. Okay, so this is an important technique in analysis where what you want to show, suppose you have to make use of some structure of this sequence or function or something. If you can manage to prove it for certain well-behaved subsequence, and then control everything else by this term, okay, like we did here. So this is an important technique. Anyway, you will probably see this many times, maybe continuity or other things, okay? So this shows that, so this is the end of the proof. Therefore, the sum 1 by n power a, when n goes from 1 to infinity, converges for a bigger than 1. Okay, so in particular, someone mentioned 1 by n squared converges. Okay, so 1 by n squared converges. Okay, a is 2. Okay, so we have determined all a. So you see that there was no ratio test, blah blah blah, all these things here. Okay, what did we use? Only basic things. What are the most important things? That's what we used. Okay, all right. So you have some. Yes.
Sir, probably we are missing something, that grouping of terms doesn't have any effect on the positive series.
Sorry, it doesn't have any effect. What do you mean?
On the grouping of terms. I mean, introducing the brackets.
Yes.
Introducing the brackets in the series with negative terms, they tend to have an effect, right?
Yeah, but that we are not dealing with negative terms here, right? I am only controlling at the level of finite partial sum. Okay,
I
so
mean,
here
my only point of concern is we did not specify that result, that grouping of terms doesn't.
No, there is no grouping of. I am not grouping terms of an infinite series in a way that there's no. I am getting bounds at a finite level. Okay, if you have a finite number of terms, you can group them however you like.
Okay, yeah. Yeah. Thank you.
Yeah. Any other questions? Okay. So far so good. And so let me just add that fourth example which I wanted to write. So now since we proved that the required things, so let's look at so we did this sequence cosine n pi by 8. We saw that this sequence is not a convergence sequence when n goes to infinity. So let me just make it a bit more nasty. This series, let's say, because I have a log n on the denominator, it starts from 2. Okay, converges or diverges?
I think
Converges.
Convergent, sir.
Convergent. Okay, so why?
By comparison test, I mean, we can say that the series is bounded above by summation 1 by n square.
Yeah.
And then
okay.
you know that summation 1 by square is convergent.
Yeah. Right. So what we are using here is the standard way to do, not the contrapositive of comparison. Standard comparison. So I just put this. Yeah. Okay. So cosine, no matter what argument is inside, cosine is always less than, in modulus is always less than 1. So this is less than 1. Denominator, at least let me write this, is less than 1 by n squared. For what kind of n? So let me just write this is true for at least n bigger than 3 or something. Okay.
Greater than or equal to 2.
Greater than or equal to 2.
This is okay. So therefore, comparison test. So remember, for a series, if you want to know that a series converges, not the value of the series, not the value of the infinite sum, but just if you want to know the series converges, there is no problem in omitting the first 10 terms or 100 terms or 1000 terms. You can omit any finite number of terms. Just look at the rest of the series. If that converges, then the original series also converges. Okay. Of course, the value of the sum will be different. You have to add the finite terms first before you can get it. But this is okay. Okay, so comparison now. So this is your mod an, this is bn. Okay, we have just seen that sigma bn converges. This is bn, this whole term is an. Okay, so comparison gives this series converges. So converges. So you see here that so even though this changes sign, okay, cosine can become cosine takes on both positive and negative values. So you cannot just directly say that this term is less than equal to 1 by n squared. What is true is in modulus, it is less than equal to 1 by n squared. Okay. Okay, so I guess that's that. So maybe just to wrap up, to just show that why everything follows from whatever we have done, let me just state a baby version of ratio test and tell you that this proof is exactly following from comparison. Okay, so ratio test. So I'm not writing the most general because that involves lim sup and lim inf, which I did not cover in these lectures. So let an be a real sequence. Suppose that we know that the limit as n goes to infinity, mod an plus 1 over mod an equal to L, which is strictly less than 1. Okay. Then the series an converges absolutely, meaning that mod an, the series of mod an converges. So this is if the limit is strictly bigger than 1, then the series an diverges. Okay, and lastly, okay, so let me write if this limit is exactly 1, then let me write, usually this is what is written, test is inconclusive. But what does this mean? I mean, this is not that, so it means that there are sequences an with this property and such that sigma an converges, and sequences bn with this property, meaning that this limit is 1, bn with the same property, but bn, the series, diverges. Okay, so therefore if you know this, it depends on the situation at hand. You have to investigate further. That's all it means. It doesn't mean that this is what you should remember. So it means that there are examples where this happens or the other scenario happens. So before you answer, you must dwell deeper and make a finer analysis in most cases when this happens. Okay, so let me just maybe I will not prove all 3 parts, but I will just prove the first part just to tell you, just to show how it follows from things we have done. Okay, so proof. So I will just prove the first part. Okay, this part. Suppose that suppose that this happens, that the ratio of the successive terms has a limit that is less than 1. Then we are claiming that the series, not only series converges, it actually converges absolutely, meaning this series mod an converges. Okay, so let's look at it. What does it mean? That since, so we have, so proof of 1, we have limit of mod an plus 1 by mod an equal to L, okay, which is strictly less than 1, n goes to infinity. So if L is less than 1, this is given to us. So since L is less than 1, we can find, let me say, maybe I will write L tilde such that L tilde lies between L and 1. Okay. So still there is a gap. You should really think of what we are using here. Okay. What is it? It's also like a kind of Archimedean property. Anyway, okay. So since there is a gap, it's a strict inequality. So we can find something that is bigger than L, but still less than 1. Okay. Then look at it, that limit of the ratio, it approaches L, but we have taken L tilde bigger than L. Therefore, there exists, let me say capital N, such that mod an plus 1 by an is less than L tilde for n bigger than equal to capital N. Is this okay?
Yes, sir.
So the limit is equal to L. So if you take something slightly larger, then all of them starting from some term onwards will be strictly less than L tilde. Okay. All right. So remember also this fact that L tilde is also still less than 1. Okay. So what does this mean? This implies, so let me write it first and then I will explain that mod an less than L tilde power n minus capital N mod a capital N. This is for n bigger than equal to. So is this fact clear? Why is it? So you want to say for all numbers bigger than capital N, this estimate is true. So you just check, okay? So let me call this relation star. So what do we have? We have, if you apply star to with n equal to capital N, we have an plus 1 in modulus less than L tilde times mod an, right? I apply star, applying star. Okay, so now if mod an plus 2, how big is this? Mod an plus 2 is less than L tilde times mod an plus 1. Again applying star with little n equal to capital N plus 1. Remember, this holds for everything bigger than equal to n. So I can apply it for capital N plus 1. But you see the previous line. Mod an plus 1, we have just done in the previous line. This is less than L tilde times this. So you have L tilde squared times mod an, mod capital An, right? And so on. So therefore, this gives you, so if you figure out for small n bigger than capital N, what is it? Therefore, you get the result, okay? Proceeding like this, you get what I have written in green. You get the estimate that I have written. Okay, that's it. So now you see, therefore, remember, we just talked about this. If you omit a finite number of terms from the series, that's fine. If the rest of the terms, if the rest of the series, if that converges, then your original series also converges. Okay, remember here, n is a fixed index. So you are looking at the series starting from n to capital N to infinity. Okay, so we have, just to rewrite this thing, mod an less than L tilde to the power little n minus capital N, a capital N. Okay, so by comparison, okay, maybe I just write one more. Since L tilde is less than 1, we know that the geometric series L tilde power n from whatever, doesn't matter. I will just simply write n to infinity just because we are Okay, 0 to infinity. This is finite. This converges because of geometric series. And now comparison gives that. So the right hand side series, this is a fixed term. This is what is varying with n, and that's a geometric series. So this comparison gives that this series of mod an also converges. So which is the same as saying an converges absolutely. That is, the series an converges absolutely. Okay, is this fine?
Yes, sir.
Yes, sir.
Okay, so you see what we have done is just again, even though you call something root ratio test or root test, ultimately it boils down to same two tools. One is geometric series, another is comparison. That's it. So okay, I hope that I have told this many times, so you must be anyway sick of hearing this. So I will just finish. There's only like 2-3 minutes, so I'm unable to do continuity. Anyway, it's fine. Divakaran will continue this. So I will just, so for 3 alone, you can prove the second part similarly. You use the contrapositive or whatever, okay? Try to prove the second part again. What is the analogous tool we have to use to prove part 2 of this result I've written? So for third one, let me just finish with example. Third one, if you look at 1 by n, okay? So, I mean, again, this is not some new example I'm writing. This is the standard example given. This diverges. We have seen that. And 1 by n squared, this series, we have just again shown this converges. But both have let me write like this, an plus 1 by an in modulus going to exactly 1. Okay. So you have this situation where two sequences, both have the same behavior as far as ratio, how the ratio behaves, successive ratio, but the behavior of the series is vastly different. Okay. So then you cannot really say anything. You just have to take it case by case. Look at the series at hand.
Sir, you are not audible.
Yeah, I think I cannot also hear him. I thought it's a problem from my side. Kaushik, you're not audible. I think let's just wait for him. It must be a power cut or some network problem.
Yeah, sorry, I got disconnected for a second.
Yeah, now we can hear you. Yes.
Yeah. I mean, okay. Yeah. So anyway, I guess people didn't have any questions, so I will stop there. Okay. So.
This was the last lecture from Kosuhik. After this, Professor Divakaran will take over the real analysis session. So we had a nice set of sessions with a lot of emphasis on how to rigorously work through the various concepts of analysis. Often the biggest complaint from students when learning mathematics is that learning mathematics is equivalent to learning a bunch of formulas, and it is usually difficult to remember so many formulas. I thank Kosuhik for reminding all of us that one doesn't really need to remember a lot of formulas to do mathematics. Usually there is a few of core theorems from which all the results follows very easily. So thank you, Kosuhik, for taking your time for the workshop.
Thanks. Yeah, you're welcome. Yeah.
I request if any of the participants have to say something, please feel free to do so.
Good evening all. Am I audible?
Yes, yes.
I'm Deepa. So let me take this opportunity to thank Kosuhik. So I'll just calling you by name with reference to your first lecture. Okay, so thank you for the thought-provoking and interesting lecture. Highly appreciable, like how you started it with the basics of real numbers, and it was just like building the blocks with supremum, completeness, Archimedean principles. Yes, and as Sir was mentioning, often students have the complaint like mathematics is always like formulas and they have to just learn it. But then maybe we can actually try this approach of bringing it intuitively. Things are coming and things will just fall into places when we follow Kosuhik's approach towards it. And thank you for the empty number of examples, especially. Often students, and as a student, like I felt like a student, listening your lectures, and often students highly appreciate the examples. So thank you for giving empty number of examples so we can just share this knowledge with our students and others as well. And special mention to spending your valuable time here with us and helping to sharing your knowledge with us and helping us to improve. Thank you.
Yeah, thanks very much. Yeah, it was a pleasure, and yeah, I hope I also enjoyed teaching all of you. So it was good, all the participation and questions that we got. So it was nice. Yeah, so thanks.
Yeah, thank you, Deepa. Is there anyone else wants to say something?
I want to.
Yeah, yes, ma'am.
I am Pratima Negi. I am from Zakir Hussain College, University of Delhi. Today I came to know that now Kosuhik sir will not be taking further session. So I personally feel that it's an honor to us that we have got opportunity to attend your odd lecture, sir. We enjoyed your odd lecture from real numbers, Archimedean property, its completeness property, then from infinite sequence to its convergence, and not now infinite series. Till you have done in 4 days, you have covered very long parts, sir. I mean, it's all syllabus in my semester system, but you have showed your patience in all that, sir. I find your lectures are more interesting because you try to get information from us, and in that way it becomes more interacting rather than just a lecture. We find it more interacting. Thank you so much, sir, for giving your valuable time and imparting knowledge to us. Thank you so much, sir.
Thanks, Pratima. Yeah. Thank you.
Yeah. Thank you, everyone. I think, yeah, we are, I think then we are good to end this session. Yeah, okay. Thank you, Kosuhik. We hope to see you sometime again. Yeah.
Yeah, of course. Yeah.
Yeah.
Thanks. Yeah.
Yeah.
Will you be there tomorrow, Kosuhik, tutorials by any chance?
Yeah, I can. Yeah. I mean, oh, tomorrow is there. Okay, I completely forgot. Yeah, I can be there like last time.
If you're free, yeah, you can.
Yeah, if I'm, so I think I'm mostly free. I'll just have to check. But yeah, I think if I'm free, I'll probably attend this until 8 o'clock or something. Is it still at 7 o'clock?
Yeah, it's same time, 7:10 to 8:10. Your
okay.
Your lecture timing. Yeah.
Okay. Yeah. So then probably I will attend like last time. Yeah.
Sure. Yeah.
Okay. Yeah. Okay. All right. Yeah. Thanks.
Thanks, Kosuhik.
Yeah. Yeah.
Thank you, everyone. Good night.